So this
Professor, sorry,
yeah,
I just have a quick question. Is that a negative WL squared or is that a whole new expression?
that's negative.
Okay, so that's a whole, is that continuing the YX equation? Okay.
Yes, that's why I'm going to show like this. So there are two terms in the expression of y of x. The first one is this coefficient WL quadruple over 16 EI U quadruple times the square bracket minus WL square over AEI U square times X times L minus X. These two parts constitute the expression of y of x. Now, once we have the expression of y of x, and what we need to do is to find out the maximum expression, right? That's what we had said that that's one of our approaches. So in step 4, we are going to explore this. Find out what is the maximum deflection here. And where do you think the maximum deflection will occur?
L over 2.
Very good. So that is y of L over 2. Which means in order to get the expression of y maximum, you just have to plug in x with L over 2 into the expression of this y of x here. So if you look at this one here, just be careful that only replace x with L over 2. U here is a constant. Not really constant, is a force dependent. So U is KL over 2. When you substitute x into here, just pay attention to the x. This will be replaced. This will be replaced. This and this. So you just have to substitute L over 2 into the locations where I mark these x in blue circles. And so how do we get that? How do we get the expression of y maximum? It's just mathematics, right? So in the end, you can write this to be pi WL squared over 384 over EI times an expression. And this expression is 12 upstairs, 12 times which way? I don't know which way. Oh, that's right, this way. 2 sec times second. U minus U squared minus 2. And then divided by 5U quadruple. The first question you must have is, why do we have to write the expression of y maximum this way? As that has something to do with the coefficient. This coefficient here. Does anyone recognize this coefficient? What is this coefficient? It looks familiar, right? So what's this coefficient? This coefficient is the maximum deflection of a simply supported beam subjected to uniformly distributed loading at midspan. Which is from here to here. This is YWL squared over 384 EI without the application of the axial force P. So the reason why we want to express y maximum this way is because by writing y maximum this way, you can actually assess the effect of axial force. Because the case when the P is 0, that expression, which is 5 times WL squared over 384 EI. Now, when we look at this, we know that to determine the condition to make the y maximum to be approaching to infinity, we look at this too. Do you think that the coefficient phi WL squared over 384 EI can be approached to infinity? Do you think so? Do you think it's possible?
No.
No, why?
Because you have to the power of fourth as a denominator. That will probably increase faster than the top.
Okay. And for this case, I will go through each coefficient one by one. So you know my reasoning process, and you're going to remember that in the future. So I will not repeat it again. Well, the first one, so let's do it together, which is to look at this, to see that can this be approached to infinity? First of all, you know that the ratio. Yes?
Yes.
How? How can this be approached to infinity?
I mean, if we have, oh, you mean, no, that's why not.
Well, let's not give up that easily.
But the WL square, that could be because like imagine if you have like the beams too long and the weight is like too high, and then that can drive up as well.
Okay, so let's finish the discussion. To make this coefficient to be approached to infinity, you either have first of all, the ratio phi over 384 is finite, so it's not going to be approached to infinity. So that one is gone. W, to make the W to be approached to infinity, then you can have y maximum to approach to infinity, correct? So you have the same argument that to consider an infinitely long beam column, correct? Or we consider infinitely large loading, correct?
Yes.
So these two conditions, unfortunately, are what we call trivial conditions, because the infinite deflection, which is the maximum deflection here, y maximum, is not caused by buckling. It's caused by your infinite loading, or by the infinite length of your beam column, which means that this is not really caused by buckling. It's not the condition to constitute buckling. Therefore, we call these two conditions trivial conditions, which means we're not going to, they are not the reason to cause buckling. And the third one is what? How to make the y maximum to be buckling by considering the first coefficient is to have E to be 0 or I to be 0. You also know that these two are also trivial, correct? Correct? Right? What's the case when E is 0? There's no material. What's the case when I is 0?
There's no material.
There's no cross-section. When E is 0, that's material's property. That means there's no material. I is about the geometry. So when I is 0, that means there's no cross-section. So these two means differently. Okay. So we know that the first coefficient, the phi WL squared over 384 EI, cannot be approached to infinity. That's confirmed, which means our only hope is the second term, which is this one here. Now let's consider this one. So we have this whole thing, which is 12 over 5. We can call it U quadruple times 2 times second U minus U squared minus 2. We want to see that can this be approached to infinity? Okay. Now, just recall that because U is KL over 2, right? So first of all, the same argument. To make this to be approached to infinity, this means first, this is the force, right? This must be 0, correct? But when this U, new variable U is 0, what does that mean? That means K must be 0. But when K is 0, what does that mean? That means P is 0.
P is 0.
Right? So what's the case when P is 0? Again,
There's no force.
There's no force. There's no loading, nothing. So this is also trivial. No, that means this guy is gone. 2 constant, drop it out. It's finite. And U square, can U square be approached to infinity? Well, if U square has to be approached to infinity, that means P has to approach to infinity, right? And that's also trivial. So this thing is also gone. That leaves us with only one term, which is 2 times second square. And 2, of course, is constant. You can also drop it out. That means we only need to look at second U. So our only hope is to see that if can second U, or you can call it second K over 2, can this be approached to infinity? The answer is yes, because second is 1 over cosine, right? That means 1 over cosine K over 2. Can this be approached to infinity? This can be approached to infinity when cosine K over 2 is 0. Now, what makes cosine K over 2 to be 0? When cosine is 0, right? Right?
Pi over 2.
Cosine 0 is not 0. Cosine 0 is what?
When it's equal to 1.
What will be the case when cosine is 0?
When KL over 2 is equal to 1.
Pi over 2.
Pi over 2.
Pi over 2.
Pi over 2.
Pi over 2, right? Pi over 2. So why do I have to ask you these questions? Maybe they may appear to be so simple and so straightforward, because when you are solving this problem on exams, and many of you may get excited because now you see you're getting to the end. Maybe you plug in the numbers too quick. You said it has to be 1. So just be patient here. How do you make sure that you are not going to make a mistake? It's easy. Just draw a diagram, right? Just draw a diagram and remind yourself that there's a triangle like this, and you say that is this. What's your cosine? Cosine is the ratio of this. What's the sine? This is the ratio of sine. What's tangent? Tangent is these two. Tangent. So what makes cosine to be 0 is when this leg to become vertical. That's cosine to be 0, which means it's pi over 2. Right? What makes sine to be 0? And when it makes sine to be 0, that means it's going to be this green line. This is sine to be 0. So this way, we know that K over 2 must be n times pi over 2. Right? So n can be any integers. So n can be any integers. Starting with the first one, that means n is 1. That leads us to the first root, which means KL over 2 must be pi over 2. Of course, that means KL must be pi, and the rest is history. You already know what we're getting at. That means the square root, you can do either way you like. P over EI must be pi over L. So what's the critical law here? Is pi square EI over L square. And not surprisingly, this equals to PE, right? So that's how we found the critical law for this problem. And many